Hi, I'm Sabin Yaakov. This presentation is entitled Basics of DSAT over Current Protection. In this presentation, I'm going to cover in a general way the concept of DSAT-based overcurrent protection, talk about IGBT output characteristic. I'll show some example of implementing the DSAT network, and then talk about circuit design and simulation by LT-Spice. Let me first of all sort of clarify terms here. I'm showing here two output characteristics of a BJT and a MOSFET. Well, they seem to be similar in quite a bit, and in both cases we have region in which the device is like a current source. Here the parameter is the base current. Here we have the collector to emitter voltage, and this is the collector current. In here, the parameter is the gate to source voltage, and here is the drain to source voltage, and this is the collector voltage. Now, the correct term of the different region is, for BJT, this region is called the active zone, okay? While this region is called the saturation. This is the terminology that is used for BJT. On the other hand, for the MOSFET, for reasons that I really have no clue why they are, this region is called saturation. Saturation meaning that the device is like a current source. The current doesn't go higher for a given gate to source voltage. And this region is called the ohmic region. Okay, so there's kind of a confusion here, because this is saturation here, and this is saturation here. And what about IGBT? Well, IGBT somehow got stuck with this arrangement here, where here we call it saturation. And the DSAT means that we are going to DSAT, that is to remove the saturation caused by a high current. That is, the concept is that we have a high current, we are locked somewhere here to a high current, and we're going to remove this saturation, and this is the DSAT. So this is the protection scheme that I'm going to talk about in this presentation. So let me show here a data sheet, or part of a data sheet of a IGBT. It's the Infineon IGBT. It's specified to ATM. Well, this is ATM, DC, etc. But just gives us the level of current of this device. And it is very important to realize that IGBTs are very robust devices. For example, you see here, it will withstand a short circuit, meaning that you can connect the IGBT to a 330 volt supply, okay, feed to the gate to emitter 15 volt, and it will withstand this situation for 5 microseconds. Well, mind you, connecting it to this high voltage with that drive, the current will be very high. It'll obviously get into the saturation region for this particular 15 volt, okay? So the IGBT is very robust. Also, it can hold on for quite a while. It's relatively a large chip. So therefore, they are compatible with the DSAT approach, which is not very fast. And here I'm showing the output characteristic of this particular device. Well, let's look at the level of 100 amp, say gate to emitter of 10 volt. We see that the voltage on the device will be 2.5 volt, while at an elevated temperature, 175, is just about the maximum junction temperature, you see that you get a much higher voltage. So we're talking now about a situation that all these values of this voltage across the collector are temperature dependent, which makes the system sensitive to temperature changes. So in general, you like to work somewhere here with regard to the DSAT approach. That is, you know what is your drive, and then you pick up the level of protection from which you get about the voltage that will be across the device when you need to disconnect it and in fact lower the gate voltage to zero. Not immediately, we'll talk about it, but this is the first step you have to do. You have to sort of locate the area that you like to work at. I'm showing now another transistor, and this is by Burns. Actually, it's specified to somewhat higher current. Again, it will withstand 300 volt for 10 microseconds, a little bit even higher. And so it's a really robust device. And here you see the characteristic is somewhat different, but in general you see that the area that you like to work it is probably somewhere here, because if you like to limit the current to some reasonable values, you're not reaching the saturation level. Okay, saturation level is much higher than that, and you don't want to go that high. So in fact, in many cases, although you call it DSAT, you are really not entering the saturation region, but you just rely on the fact that the higher the current, the higher is the collector voltage, and therefore you can detect it and then disconnect the gate or lower the voltage of the gate. Let me talk now a little bit about shorts. Well, there are many kinds of shorts. I'm showing here, for example, a short to the bus voltage. Okay, in fact, there is a standard in which you have to expose an inverter to this type of a short. So we connect the bus directly to the midpoint, so when this transistor is on, well, there's surely a short. I'm showing an inductance, not because there is an inductor, just to emphasize that any wire will have inductance to it. And as it turns out, the inductance makes a big difference of the voltage across the transistor during this short period or episode. So there is an inductance here, there's also an inductance in between these two. This is sort of representing a generic half bridge, could be an inverter, a rectifier, or any other circuit. And then we can recognize a number of situations of shorts. There is an outside short, this is a short like this, could be a shoot-through short like this between the two transistors, could be a short at, say, upper transistor. Suppose this is damaged, you turn on this against a short, and could be a short indeed as you turn on the transistor. Already you have the short, or you can turn on the transistor and then after a while you might have a short, not necessarily at the very beginning of the gate pulse. And the SAT circuit has to sort of accommodate these two possibilities and to give a protection in each case. And then we have to take into consideration that the inductance involved with the short is very important, that is the magnitude of the inductance. So suppose we have a certain transistor, and this will be, say, the nominal operating point, and I'm choosing to I choose to limit the current to around, say, 180 amp. So in the nominal case, we are going to have 1.5 volt, and here we're going to have something like 2.3 volt. So our circuit has to be able to distinguish between two voltages, and when it is below 2.3 volt, then it shouldn't activate the turn off of the gate. Okay, it should turn it off only if the voltage across the transistor is above this value. Of course, you can choose another point. This is just an example. No way it's optimized. It's just for demonstration. So let's talk now about another issue, and that is blanking. And I'm now considering, say, a practical circuit, say half a bridge. We could have a situation in which current is coming out of the midpoint or into the midpoint. Let's take, for example, this case in which the current is coming in, and let's assume that we are in the stage that this transistor is on, so the current is passing through the transistor. Voltage across the lower transistor is high, and then we turn off this transistor so the current is passing through the diode, okay? And then after that time, we're going to turn on this transistor, okay? Now we turn on this transistor against this conducting diode, so the current will start building up, and the current of the diode, of course, will decrease now because we are sort of consuming current here, up to the point that all the inductor current is going here, and then we're going to have the reverse current. I'm showing it here. Only then the voltage here will start dropping. So if I look at this transistor that I might wish to protect, at the very beginning of the pulse, there is a high voltage on it. Okay, at the very beginning here is the high voltage. So if this DSAT network will be operational, it will turn off the transistor. So I need the blanking time until the voltage here drops to the nominal value, 2 volts or something like that, and only then I can allow the DSAT circuit to actually operate. So we need a blanking. That's one of the requirements. So now we come to the actual driver with the actual DSAT circuit. This is an example of a TI driver. By no means there is a recommendation here, just an example, a demonstration. There are other companies who are making similar drivers. And in this particular case, we have this pin here, this terminal here, the overcurrent, and a comparator connected in this side to 0.7 volts, fairly low voltage, such that if the voltage at this OC is higher than 0.7, this will be activated and will turn off the transistor that is feeding this is the outside transistor. We'll turn it off. This belongs to the circuit for some reason. They didn't put it in, I don't know why. Anyhow, it'll turn it off and actually activate this transistor, which is the turn off path here. So the current now is flowing this way, actually reducing the voltage of the gate. Okay, so this circuit now, this network, is actually doing this function of the DSAT by this diode, the network. This is the power supply. This is the sense point. Here is a filter capacitor, you might say. Actually, it's a timer also. And then there are some resistors. You don't have to use all of them. You can get by without this one. And I'm not going into the very fine details, just to explain in a general way what is this circuit all about. So let's understand how does it operate. At the very beginning, when the feed transistor, the on transistor, is off, then the capacitor is actually being discharged or shorted out by this FAT here. Okay, this is prior to the gate turning on, this point here. At this point, the voltage across the outer transistor is high, so this is the starting point. Now, I'm turning on the upper, I'm not showing it anymore, I'm turning on this upper transistor that is feeding here the gate. Okay, this short is released and the capacitor starts to charge. This is providing now the blanking, because as long as the voltage across the capacitor is low, then of course it will not reach the trigger point, which is 0.7. So this is actually now the blanking process. Meanwhile, the voltage across the transistor that we are protecting or wish to protect is starting to go down. It is going down while the voltage here is going up. This is the voltage here at the sense point. So eventually the voltage here will go all the way to the nominal collector voltage, say 2 volts. The diode will be conducting, which also will contribute to a attenuation of this point, and this will level off at a given point, and it should be designed such a way that when the voltage across the MOSFET that I'm protecting is the nominal one, it's OK voltage, it should be below 0.7. And if the current is high and the voltage goes up, it should cross the 0.7, and then the circuit will be activated. Here they are actually showing in the data sheet the process, and what we see here is actually a case in which there is a short at the beginning. Okay, so we see here the capacitor, I guess, charging, and then it goes above the 0.7. There is some delay here, and then the circuit is activated, and this is the gate, and now the gate is going down. But notice that in this particular driver, it doesn't go down immediately, but rather in 2 steps. If you turn off the gate very quickly, you turn off the current very quickly, and then you're going to have a very large voltage due to the IDT of this high current. So therefore, in more sophisticated drivers, it is gradual, and the simplest thing is, say, to have 2 steps. So you first go to this level here, stay there for a while, and then you go to the lower level. By this, you sort of smooth out the voltage spike due to the fact that you are interrupting a very high current. This is a side story, has nothing to do with the DSAT, of course, but it is a very nice and important feature. So we understand now how it works. Basically, at the beginning, the voltage of the capacitor is 0, you charge it, you come to a point that you are ready for detection, and then depending on the voltage across the transistor, you develop a voltage here, affecting the voltage here, and then the circuit will be activated if the voltage of the collector is above a given potential. Now, there are many components here. You don't have to use all of them, as I've said, but there's a lot of such a degree of freedom here, and just to write equations, it's lengthy and very tiresome. So I think the best way to do is to do some very rough calculation about the magnitude of the resistances that you like to have, and then in the divider, and then to go to simulation and sort of tune the circuit for the particular case that you like to, the particular transistor and levels that you like to protect. So the design step will look something like this. First of all, we have, of course, to decide what is the voltage, which is the borderline between proper and overcurrent case. And then there is a consideration that you'd like actually to have large resistances, not to drain the power supply, the auxiliary power supply. On the other hand, you like to have small resistances, which would mean a larger capacitor, to have a better noise immunity, so that the noise injected here will not develop that much because of the low impedance. And then we need sufficient blanking time, and also we need a fast response when the fault is within the on time, that is not just at the beginning. So, as I've said, considering all this, doing simulation is probably the best way to do. And here I'm demonstrating just general points here of a simulation circuit. Now this is an equivalent circuit, doesn't have the transistor itself, but something that emulates it. What I have here is a power supply. I have the basic networks. Notice that I've eliminated this resistor, just a diode, which should be a high voltage diode, of course, because the voltage here is very high, the fast high voltage diode. And then I have some values here, which I've already chosen, of course. I'm going to demonstrate them. And then I can emulate the behavior of the collector voltage by a dependent current source. This is piecewise linear source that is programmed to start with 400 volts, it's the voltage on the transistor at the beginning, then to drop to whatever level. Well, 2 volt is, I'm assuming, is okay, and 3 volt is already overcurrent, okay? So 2 volt is okay, and then at this point it will go to higher voltage just to emulate the case in which you have at the middle of the on-time high current, which will cause a high voltage across the transistor. So here it is. This is now the voltage source that emulates the transistor. Let me zoom in. And here is a case in which I'm dropping to 3 volt. 3 volt is supposed to be above the protection level. Okay? Here 0.7 is the protection level. This is the input to the DSAT circuitry over current circuit. I'm starting with 0 voltage across the capacitor. It's building up, and at this point, after whatever, it's like 4.3 microseconds, this is actually the blanking time here, okay? There is a blanking time due to the charging of the capacitor. Here it hits the 0.7 and the DSAT should be activated. Okay, so this is a case in which there is a short at the on of the gate, at the on instant. On the other hand, here I'm showing a case in which you start with no short, there's no short, going down to 2 volts. So here is the blanking, and here I'm sort of getting to a steady state below the 0.7 volt because I'm at 2 volt. And then here the voltage goes up due to the current, supposedly, and at this point it hits the 0.7 volt and the circuit will be activated. And for this particular case, this demo circuit, the voltage will be 4 volt when the actual action will be taken, because there are delays, and as I've said, IGBT can tolerate some of these delays because it's very robust. Other transistors like gallium nitride may not be able to sustain this stress. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.